You are drifting through darkness that existed before the sun, before Earth, before any world we know had taken form in the empty reaches of space. Your spacecraft floats within a vast cloud of gas and dust, a nebula stretching outward in every direction farther than light could travel in years. Through the viewing ports, you see almost nothing at first, just the faintest haze of material, illuminated by distant stars scattered throughout the Milky Way galaxy. This is the birthplace, the beginning, the moment 4.6 billion years ago, when our solar system existed only as this quiet, formless expanse. Hidden within this silent cloud are the ingredients of planets, moons, oceans, mountains, and eventually, life itself. Everything that would one day become our cosmic neighborhood is suspended here, scattered throughout this vast nebula of gas and dust. Gravity has not yet gathered this material into stars, planets, or moons, but the process is about to begin. The cloud contains mostly hydrogen and helium, the simplest and most abundant elements in the universe, inherited from the creation of everything in the beginning. And mixed within this gas are tiny grains of dust, particles of heavier elements like carbon, oxygen, silicon, and iron, forged inside stars that lived and died long before this moment. These dust grains drift through the hydrogen, so small that trillions could fit within a handful of sand. Barely visible on their own, yet many will one day become part of worlds that do not yet exist. Worlds still hundreds of millions of years in the future. The temperature here measures only 10 to 20 degrees above absolute zero. Cold beyond anything you experience on Earth. Cold enough to freeze almost every substance into solid ice. You are listening to the Drowsy Astronaut, and tonight we travel together through the complete story of our solar system, from this ancient beginning to its final days, trillions of years ahead. We will move slowly through this journey, taking time to see what exists at each stage, to understand how everything came to be, and how it will all eventually end. If you are listening from somewhere on Earth tonight, feel free to share where you are in the comments. And if you find this journey calming and worthwhile, a like or subscription helps us continue making these slow explorations through space and time. Now we return to the nebula, to this cloud floating silently in the darkness, waiting for something to begin. The scale of this cloud defies easy comprehension, stretching across several light years of space, thousands of times wider than the solar system that will eventually form from its material. If we could see the entire structure at once, it would appear as a dark patch against the background stars, blocking their light where the dust concentrates most thickly. Within the cloud, the density remains incredibly low by Earth standards, far thinner than the best vacuum we can create in any laboratory, yet dense enough by the standards of interstellar space. Billions upon billions of tons of material drift here, spread across this vast volume, moving slowly under the weak pull of its own collective gravity. The cloud has been here for a long time already, perhaps millions of years, drifting through this region of the galaxy as part of the Milky Way's slow rotation. It formed from material expelled by earlier generations of stars, some of which ended their lives in supernova explosions that scattered their enriched contents into space. The hydrogen and helium came from the beginning of the universe itself, created in the first few minutes after the Big Bang 13.8 billion years ago. The heavier elements, everything else we see mixed into this cloud, came from nuclear fusion inside stars and from the violent deaths of massive stars. This mixture of ancient hydrogen and recycled stardust makes up everything that will eventually become the sun, the planets, the moons, the asteroids, and eventually us. From our vantage point within the cloud, we can occasionally glimpse other stars through the haze, their light reaching us from distances measured in dozens or hundreds of light years. Some of these stars are young, newly formed from their own collapsing clouds, shining brightly in blue and white as they burn through their fuel at tremendous rates. Others are older, cooler, redder stars that have been shining steadily for billions of years and will continue for billions more before they die. One of these distant stars might be the source of the disturbance that will soon trigger this cloud's collapse, though from here we cannot yet tell which one. The galaxy continues its business around this quiet place, indifferent to what is about to begin. The dust grains floating through the hydrogen carry special significance, even though they make up only about 2% of the cloud's total mass by weight. These particles will serve as the seeds around which larger structures can grow, providing surfaces where atoms and molecules can stick together and accumulate over time. Each grain measures less than 1/millionth of a meter across, smaller than the smallest mote of dust visible to the human eye. Yet there are countless trillions of them distributed throughout the cloud. Some grains are made of carbon, resembling soot or graphite, dark and absorbent of any light that touches them. Others consist of silicate minerals, compounds of silicon and oxygen, mixed with metals, similar to the materials that will one day make up rocky planets. Still others are coated in ices, frozen water, and methane and ammonia, substances that will become crucial in the formation of worlds farther from the sun. The silence here is absolute, deeper than any silence experienced in places where atmosphere exists to carry vibrations we call sound. Space offers no medium for sound waves to travel, no air molecules to compress and expand, so even if massive events were occurring nearby, we would perceive only the visual evidence. The cloud itself makes no sound as it drifts, no whisper as particles brush past one another in the nearly perfect vacuum. This quietness feels ancient, primordial, as if this place exists outside of time, waiting in a stillness that has persisted for ages beyond counting. Yet despite the appearance of permanence, this cloud cannot remain in this state forever. Held in a delicate balance between the weak inward pull of its own gravity and the slight outward pressure from the motion of its gas particles. Gravity wants to draw all this material together into a smaller, denser configuration, while the random movements of atoms provide a tiny resistance against collapse. For now, the balance holds, but it is fragile, requiring only a small disturbance to tip the cloud toward a different fate. Something will soon provide that disturbance, breaking the equilibrium and setting in motion everything that follows. Somewhere beyond our view, perhaps a few dozen light years away, a massive star has reached the end of its life after burning fiercely for only a few million years. Its core has run out of fuel to sustain the nuclear fusion that held it up against gravity's relentless inward pull. Without that outward pressure from fusion, the core collapses catastrophically in a fraction of a second, then rebounds in a supernova explosion that tears the star apart. The explosion releases more energy in a few weeks than our sun will produce in its entire 10 billion year lifetime. And that energy propagates outward as a shockwave traveling through space at a significant fraction of light speed. The shockwave moves through the interstellar medium, pushing gas and dust ahead of it like a cosmic plow clearing a field. It sweeps through the sparse material between stars, creating expanding bubbles and shells of compressed gas wherever it passes. Eventually, after traveling for years through the near emptiness of space, the shockwave reaches the outer edges of our nebula, where it begins to compress the cloud's material at the boundary. This compression is gentle by human standards, exerting no more force than a light breeze, but in the delicate balance of the nebula, even this subtle push proves sufficient. The outer layers of the cloud begin to compress, and as they do, their density increases slightly, which means their gravitational pull on neighboring material strengthens just a little. This stronger gravity pulls in more material, which increases density further, which increases gravity more, creating a feedback loop that builds on itself. The cloud begins to contract, not everywhere at once, but in certain regions where the density happens to be slightly higher than average. Our spacecraft drifts within one of these regions, a portion of the cloud that holds enough mass to eventually become an entire star system. As the contraction begins, the process remains almost imperceptible at first, with the cloud's radius shrinking by only tiny fractions over thousands of years. The material falls inward so slowly that if we watched for a human lifetime, we might not notice any change at all. But time and space operates on scales unfamiliar to brief human lives, and processes that seem infinitesimally slow still accomplish profound transformations given enough centuries and millennia. The cloud that appeared eternal and unchanging has begun a journey that will not stop until a star ignites at its center and planets orbit in the surrounding disk. From our position within the contracting cloud, we might notice the background stars becoming slightly more obscured over long periods as the material around us grows denser. The dust grains pass by our spacecraft more frequently, still separated by vast distances, but not as vast as before. The temperature begins to rise, imperceptibly at first, adding a single degree here and there over thousands of years as gravitational potential energy converts to heat. The cloud's self-gravity grows stronger as material packs closer together, accelerating the inward fall in a process that feeds on itself. The cloud also possesses a slight rotation, barely noticeable at first, inherited from the general motion of gas in this region of the galaxy. As the cloud contracts, this rotation becomes more significant, following a fundamental principle of physics called conservation of angular momentum. Just as an ice skater spins faster when pulling their arms inward, the cloud spins faster as it shrinks, even though no external force acts to speed up the rotation. The material begins to swirl as it falls, creating currents and streams within the collapsing cloud that will soon organize into a more structured configuration. The collapse is not perfectly uniform, with some regions falling faster than others, depending on their initial density and position within the cloud. Material near what will become the center falls fastest, pulled by the strongest gravitational attraction from all the mass surrounding it. Material further out falls more slowly, still responding to gravity, but also influenced by the developing rotation of the cloud. The result is a complex, dynamic flow of gas and dust, all moving inward and beginning to spiral around a common center of mass. Over hundreds of thousands of years, the cloud transforms from a roughly spherical shape into something flatter, a disk forming perpendicular to the axis of rotation. Material falling toward the center cannot all arrive at the same point simultaneously, so it settles into orbits around the center, circling while continuing to slowly spiral inward. The disk grows denser and more defined with time, fed by material still falling in from the outer reaches of the original cloud. This disk will become the birthplace of planets, the structure from which all the worlds of our solar system will eventually assemble. At the very center of this collapsing disk, material accumulates faster than anywhere else, building up into a dense concentration that will become the sun. The pressure and temperature here begin to climb as more and more mass packs into a smaller volume, with gravity compressing the hydrogen and helium into an increasingly dense sphere. Heat builds slowly, the result of gravitational energy converting to thermal energy as particles fall inward and collide with growing frequency. The center glows faintly with infrared radiation, invisible to human eyes, but detectable by the warmth it would provide if we could approach close enough. This central condensation, this proto-sun forming at the heart of the disk, does not yet produce energy through nuclear fusion in its core. It shines only from the heat of its own collapse, from the gravitational energy released as material falls onto its surface from the surrounding disk. The temperature rises toward the millions of degrees required for fusion to begin, but that threshold still lies tens of thousands of years in the future. For now, the proto-sun grows larger and denser and hotter, pulling in more material every moment, building toward the mass it will need to ignite. We drift here in the disk, watching material stream past our spacecraft toward the brightening center, witnessing the slow transformation of a cloud into the beginnings of a stellar system. The dust grains that once floated in near isolation now pass close enough to occasionally collide with one another, sticking together when they touch, beginning the long process of accumulation. In the darkness around the faint glow of the proto-sun, worlds are beginning to take shape, though they remain invisible, scattered in pieces too small yet to notice. This is the birthplace not just of one star, but of an entire system, and the story has only just begun. The collapse of the nebula continues around us, material streaming inward from the vast outer regions toward the growing density at the center, where the proto-sun slowly builds its mass. Our spacecraft rides along with this inward flow, spiraling gradually toward the heart of the forming system while maintaining a safe distance from the densest concentrations. Through the viewing ports, we watch as the structure of the disk becomes more pronounced and organized with each passing millennium. What began as a diffuse cloud has transformed into something with clear geometry, a flattened disk of gas and dust rotating around a bright central bulge. The rotation of the system has grown more obvious as the collapse proceeded. with material now circling the center in well-defined orbits rather than simply falling straight inward. Conservation of angular momentum continues to govern this motion, ensuring that as the system contracts, its rotation rate increases proportionally to maintain the same total angular momentum. The disk spins like a vast cosmic whirlpool, with inner regions orbiting faster than outer regions following the same laws of gravity and motion that will later govern the orbital periods of planets. Material in the innermost disk completes an orbit in a matter of weeks or months, while material far out in the outer disk takes centuries. Gravity has sorted the material by location according to temperature and density, creating zones within the disk that will ultimately determine what kinds of objects can form at each distance from the center. Close to the proto-sun, where our view is brightest, temperatures have climbed high enough to vaporize most materials except the hardiest substances, like rock and metal. Water ice cannot exist here as solid, nor can methane, ammonia, or other volatile compounds, all of which remain as gas in the intense heat. Only particles of silicate rock and grains of metal can survive in solid form this close to the central fire. Farther out from the center, where temperatures drop significantly, we find a transition region where water ice begins to condense onto dust grains, adding a coating of frozen water to the rocky particles drifting through space. This boundary, located somewhere around 3 to 5 times Earth's eventual distance from the Sun, marks a crucial divide that scientists will later call the frost line or snow line. Beyond this line, ice can exist as solid, which dramatically increases the amount of solid material available for building planets. The frost line will determine which worlds become small and rocky, and which become massive giants wrapped in thick atmospheres of hydrogen and helium. We maneuver our spacecraft outward through the disk, crossing from the hot inner region toward the colder outer zones, watching the character of the material change around us. The dust grains passing by our windows now carry visible coatings of white ice, their surfaces frosted with water and other frozen volatiles. These icy grains are more numerous than the rocky grains alone, and they prove stickier when they collide, adhering to one another more readily than bare rock. The abundance of ice beyond the frost line means that objects forming here will have access to much more building material than objects forming closer to the Sun. The disk extends outward to hundreds of astronomical units from the center, with 1 astronomical unit being the average distance Earth will eventually orbit from the Sun, about 150 million kilometers. At these great distances from the proto-Sun, temperatures hover only slightly above the cold of interstellar space, and nearly everything freezes solid except hydrogen and helium, which remain as gas even in this deep cold. The outer disk is darker, less affected by the light and heat from the center, a realm where ice dominates and where the future giant planets will assemble. Everywhere in the disk, particles are colliding with one another, sticking together when they meet, slowly building larger aggregates from the microscopic dust grains. This process begins with electrostatic forces, the same kind of static electricity that makes dust cling to surfaces on Earth, allowing tiny particles to adhere when they touch. 2 grains stick together to form one slightly larger grain, which then collides with another grain, adding to its mass. Over thousands of years, these accumulations grow from dust mote size to pebble size, then to boulder size, building mass grain by grain. Gravity plays little role in this initial accumulation because the particles remain too small for their gravitational attraction to one another to matter. A dust grain has essentially no gravitational pull on another dust grain, so they stick together only when physical contact occurs, and electrostatic forces bind them. But as particles grow larger through continued accumulation, eventually reaching sizes of hundreds of meters or kilometers across, their gravity becomes relevant. Once that happens, the growth process accelerates dramatically in what scientists call runaway accretion, where larger objects begin pulling in nearby material actively rather than waiting for chance collisions. In the inner disk where we started our observation, the material consists mostly of rock and metal with very little ice, limiting the total amount of solid material available. Objects growing here will remain relatively small, unable to accumulate enough mass to gravitationally capture the surrounding hydrogen and helium gas. These will become the rocky planets, worlds like Mercury, Venus, Earth, and Mars, dense and solid, but modest in size. The process of assembling these worlds will take tens of millions of years, a long time by human standards, but remarkably quick in cosmic terms. In the outer disk beyond the frost line, the abundance of ice provides much more solid material for objects to accumulate, allowing them to grow far larger than anything forming in the inner regions. As these icy bodies reach masses of perhaps 10 times Earth's mass, their gravity becomes strong enough to capture and hold on to the hydrogen and helium gas drifting around them. This captured gas will form thick atmospheres of light elements, building up into massive envelopes that eventually contain hundreds of times more mass than the solid cores beneath them. These will become the gas giant planets, Jupiter and Saturn, worlds dominated by hydrogen rather than by rock. The proto-sun continues to grow at the center of all this activity, now containing more than half of the nebula's original mass, compressed into a sphere roughly the size of the current sun's orbit around the galaxy's center. Heat in its core continues to build as gravitational compression proceeds, raising the temperature toward the threshold where nuclear fusion can begin. The proto-sun shines now with perhaps 1% of the luminosity our sun will have once fusion starts, glowing from gravitational energy alone. Its surface shows swells and irregularities, turbulent motions in the not yet stable atmosphere of this forming star. Around the proto-sun, material continues to fall inward from the disk, landing on the star's surface and adding to its mass in a process called accretion. This accretion is not smooth or steady, but occurs in clumps and streams, with material spiraling in along magnetic field lines that extend from the proto-sun into the surrounding disk. When material crashes onto the star's surface, it releases energy as heat and light, creating bright spots that come and go as accretion rates vary. The young star flickers and flares irregularly, nothing like the stable, steady sun we will see billions of years later. The disk itself glows faintly in infrared light, warmed by radiation from the proto-sun at its center, and by the heat generated from friction as particles collide and material slowly spirals inward. From far away, the entire structure might appear as a dark silhouette against background stars with a bright point of light at the center. The classic appearance of what astronomers call a protoplanetary disk. Thousands of such disks exist throughout our galaxy at any given moment, each one a stellar system in the process of birth. each one following the same general path from cloud to disk to star and planets. We watch as streams of material in the disk develop subtle patterns, concentrations and gaps beginning to form at certain distances from the center. These patterns arise from complex interactions between the gravity of growing planetesimals and the gas and dust still orbiting around them. Where larger objects have formed, they clear out zones in the disk by accreting nearby material or by gravitationally flinging smaller particles into different orbits. These gaps will widen over time as the planetesimals grow into protoplanets, creating the ring-like structures that will eventually define the spacing between planetary orbits. The timescale of these processes stretches across hundreds of thousands of years, with the entire sequence from initial collapse to stable disk configuration taking roughly 500,000 years. We observe this transformation as if time has been compressed, watching millennia pass in moments, seeing the grand architecture of the solar system take shape from formless gas and dust. The cloud that seemed eternal has given way to organized structure, rotation, temperature zones, and the beginnings of solid bodies, all arranged around the growing light at the center. As the proto-sun's mass approaches the threshold needed for fusion, its core temperature climbs past 1 million degrees, then several million, then approaches 10 million degrees Kelvin, where hydrogen nuclei move fast enough to overcome their electrical repulsion. The pressure at the core grows immense, atoms packed so tightly that matter reaches densities more than 100 times that of water. Everything is building toward a moment of transformation, a threshold that will change everything. And in the disk around this almost star, worlds are slowly gathering themselves together from scattered dust. Deep within the proto-sun, at the very center, where pressure and temperature have climbed to levels incomprehensible by human standards, conditions approach the threshold for nuclear fusion. Our spacecraft maintains a safe distance from this forming star, but instruments allow us to peer inward through the layers of gas, toward the core, where hydrogen nuclei are being forced together by the immense gravitational weight of all the material above. The core temperature has reached roughly 10 million degrees Kelvin, hot enough that atoms have been stripped of their electrons, existing as bare nuclei in a plasma of incredible density and energy. At these temperatures and pressures, hydrogen nuclei move fast enough to occasionally collide with sufficient force to overcome the electrical repulsion between their positive charges. When two protons, the nuclei of hydrogen atoms, come close enough, the strong nuclear force takes over from the electromagnetic force and binds them together. Through a series of steps involving other particles and intermediate stages, 4 hydrogen nuclei eventually combine to form one helium nucleus. The mass of the helium nucleus is slightly less than the combined mass of the 4 hydrogen nuclei that created it. And this missing mass converts directly into energy, according to Einstein's famous equation. The energy released by each fusion reaction is tiny by everyday standards. But when countless trillions of these reactions occur every second throughout the sun's core, the total energy output becomes staggering. This energy begins as gamma-ray photons, the highest energy form of light, which immediately collide with surrounding particles and transfer their energy as heat. The heat creates pressure that pushes outward from the core, and this outward pressure begins to balance the inward pull of gravity that has been compressing the star. For the first time, the proto-sun achieves equilibrium. no longer collapsing, but held in a stable balance between gravity's inward pull and fusion's outward push. The moment of ignition is not dramatic from outside, not an explosion or sudden brightening visible across the disk. Instead, the proto-sun gradually transitions from gravitational heating to fusion heating over thousands of years, with the energy source shifting smoothly from collapse to nuclear reactions. The star's luminosity increases, slowly but steadily, as fusion ramps up in the core, and the surface temperature rises as more energy flows outward from the center. The color of the light shifts slightly from red toward yellow as the surface heats, though the disk's dust still obscures much of the star from outside view. Fusion begins only in the core, where conditions are extreme enough, leaving the outer layers of the star to transport this energy toward the surface through radiation and convection. Photons created in the fusion reactions bounce endlessly between particles, absorbed and re-emitted countless times as they work their way outward through the dense interior. A single photon may take tens of thousands of years to travel from the core to the surface, even though the distance is only a few 100,000 kilometers. This energy eventually emerges as light and heat from the sun's surface, the photosphere that glows with the characteristic yellow light of a stable star. We observe from the disk as the newborn sun settles into its stable configuration, its size now determined by the balance between gravity and pressure, rather than by ongoing collapse. The sun has reached what astronomers call the main sequence, the long, stable phase that will last for approximately 10 billion years, during which fusion proceeds steadily in the core. Our sun will spend the vast majority of its lifetime in this phase, converting hydrogen to helium at a rate of several 100 million tons every second, releasing enough energy to illuminate and warm the worlds forming around it. But the young sun does not behave exactly like the stable star we know from billions of years later. In this early phase, the sun displays more variability, more violent activity on its surface and in its atmosphere. Massive flares erupt from active regions, releasing bursts of energy and charged particles into the surrounding space. The sun's rotation is faster now than it will be later, spinning perhaps once every few Earth days, and this rapid rotation combined with convection in the outer layers generates powerful magnetic fields. These magnetic fields extend outward from the surface, threading through the inner disk and interacting with the charged particles there. The young sun also produces a powerful stellar wind, a stream of charged particles flowing outward from its surface in all directions. This wind is much stronger than the relatively gentle solar wind the mature sun will emit, powerful enough to have dramatic effects on the surrounding disk. In the inner regions close to the sun, this wind exerts pressure on gas atoms, pushing them outward and gradually clearing the lightest elements from the area near the forming rocky planets. Hydrogen and helium are swept away from the inner system, leaving behind only the heavier elements that will make up the terrestrial worlds. From our spacecraft's position in the disk, we can sense this wind as it streams past, an invisible flow of electrons and protons moving at hundreds of kilometers per second. If our craft carried instruments to measure magnetic fields and charged particles, they would register intense activity, the space around the young sun crackling with energy. This environment is hostile to anything delicate. Radiation levels far higher than they will be in the calmer era to come. The forming planets must weather this storm as they grow, the inner worlds losing their initial atmospheres of captured hydrogen to the relentless push of the solar wind. The disk itself begins to change in response to the sun's ignition, heated from within by the star's radiation. The inner disk grows warmer, with temperatures rising at all distances as the sun's luminosity increases beyond what gravitational collapse alone had provided. Ice lines shift outward slightly as the increased heat pushes the regions where different substances can freeze solid to greater distances from the center. Some materials that had condensed as solids now vaporize again, altering the composition of the dust available for building planets in certain zones. The combination of solar wind and radiation pressure starts to clear the disk from the inside out, pushing gas and fine dust outward or causing it to fall onto the sun. This clearing process is not instantaneous, but proceeds over millions of years, gradually thinning the disk as material either accretes onto growing planets, falls into the sun, or is driven out of the system entirely. The disk's lifetime is limited, with most protoplanetary disks observed around other stars, lasting only a few million years before the gas disperses, leaving behind whatever solid bodies managed to form during that time. We witness the sun moving through a phase astronomers call the T-Tauri phase, named after the first star of this type that was studied in detail. T-Tauri stars are young sun-like stars that have begun fusion but have not yet settled into the calm, stable burning of middle age. They show strong stellar winds, intense magnetic activity, dramatic brightness variations, and powerful jets of material that shoot outward from their poles along magnetic field lines. Our sun likely passed through this phase for a few million years, energetically clearing its surroundings, while the planets continued to form in the disk around it. The light from the young sun illuminates the disk material in striking ways, creating shadows and brightness variations depending on the density and distribution of dust. Regions where dust has been cleared appear brighter, allowing the sun's light to shine through, while dense concentrations of dust create dark lanes and shadows. If we could view the system from far away at an angle, we might see a complex pattern of rings, gaps, and spiral structures, the intricate architecture created by the interplay between gravity, light pressure, and the forming planets hidden within the disk. In this environment, planetesimals continue to grow, now bathed in the sun's light and heat, rather than forming in the cold darkness of the pre-fusion era. The rocky worlds of the inner system accumulate mass through impacts, with smaller bodies crashing together to form larger ones in a violent process of merger and accretion. Each impact releases tremendous energy, heating the growing planets and sometimes melting them entirely, creating magma oceans on their surfaces. The heat from these impacts, combined with radioactive decay of unstable elements in the rock, keeps the young planets molten, allowing heavy elements like iron to sink toward the center, while lighter rock floats toward the surface. Beyond the frost line, the process of giant planet formation continues, with massive cores of ice and rock pulling in enormous envelopes of hydrogen and helium from the surrounding disk. Jupiter grows rapidly, becoming the dominant object in the outer system aside from the Sun itself, its gravity beginning to influence the orbits of everything nearby. The giant planet's formation will have profound effects on the rest of the solar system, shaping the asteroid belt, influencing the orbits of other planets, and potentially protecting the inner worlds from excessive bombardment by comets from the outer reaches. The Sun's fusion has now established the energy source that will power the solar system for billions of years to come. providing the light and heat that will eventually enable life on Earth. From this moment forward, the sun will shine steadily, its output gradually increasing over geological time, but remaining stable enough to allow worlds to cool, atmospheres to form, and complex chemistry to develop on at least one planet's surface. The ignition is complete, the star is born, and around it the planets continue their slow assembly from the materials left over from the star's formation. We position our spacecraft in the inner region of the solar disk, within the volume of space that extends from the young sun outward to perhaps 4 astronomical units, the zone where the rocky planets Mercury, Venus, Earth, and Mars will eventually form. The environment here differs dramatically from the cold outer reaches of the disk, bathed in intense light and heat from the sun now shining steadily at the center. Temperatures range from over 1000 degrees Kelvin close to the sun to a few hundred degrees farther out, hot enough that water and other volatile compounds cannot exist as solid ice, but must remain as vapor. The material drifting through this region consists almost entirely of rocky silicate grains and particles of metal, mostly iron and nickel, the only substances that can remain solid at these temperatures. These particles make up perhaps 1% of the original nebula's mass, with the other 99% being hydrogen and helium that cannot be captured by the small bodies forming here. This limitation on available material means the rocky planets will necessarily remain modest in size, unable to grow large enough to gravitationally hold on to an atmosphere of light elements the way the giant planets farther out will. The dust grains have been colliding and sticking together for millions of years already, building from microscopic particles to pebbles, to boulders, to mountain-sized objects, through the slow accumulation of countless impacts. Objects in this size range from meters to kilometers across are called planetesimals, and they represent the intermediate stage between dust and planets. The inner disk now contains perhaps millions of these planetesimals, each orbiting the sun independently, each occasionally colliding with others in encounters that determine whether they grow larger or shatter back into fragments. Gravity begins to dominate the growth process at this stage, with larger planetesimals pulling in smaller ones from their vicinity, sweeping up material from the regions around their orbits. The largest objects grow fastest in a runaway process where increasing mass leads to stronger gravity, which leads to faster growth, which leads to even stronger gravity. Over hundreds of thousands of years, a few objects in each region of the inner disk grow to dominate their neighborhoods, becoming protoplanets several hundred to few thousand kilometers across, massive enough to significantly perturb the orbits of smaller bodies nearby. From our spacecraft, we watch one of these collisions unfold between 2 large planetesimals, each perhaps 100 kilometers in diameter, their orbits gradually converging over many years. They approach each other at several kilometers per second, their mutual gravity bending their paths toward one another, ensuring that a close encounter or impact becomes inevitable. When they finally collide, the impact releases energy equivalent to billions of nuclear weapons, vaporizing rock at the point of contact and sending shockwaves through both bodies. The collision is violent enough to partially melt both objects, which then merge together into a single larger body, a growing protoplanet that will continue to accumulate mass from its surroundings. These impacts are not rare events, but occur constantly throughout the inner disk, thousands happening every year as planetesimals of all sizes crash together, stick together, or shatter, depending on the angle and speed of impact. The space between the young sun and the frost line becomes a shooting gallery where objects strike one another repeatedly in a chaotic dance of destruction and creation. Some impacts result in accretion, adding mass to growing planets, while others are energetic enough to destroy both bodies, sending fragments careening away to potentially collide with other objects elsewhere in the system. The largest protoplanets become hot from all this violence, their surfaces glowing red or orange from the heat of impacts and from the decay of radioactive elements mixed throughout their rock. Material falling onto a protoplanet's surface converts its kinetic energy to heat on impact, delivering enough energy to melt the surface layers, and sometimes the entire body. In these molten states, the protoplanets undergo differentiation, with heavy elements like iron sinking toward the center, under gravity, while lighter silicate rock floats upward. This process creates the layered structure we see in rocky planets today, with dense metallic cores surrounded by rocky mantles and thin crusts. We observe the region where Earth is forming, watching as a Mars-sized protoplanet that will later be called Theia approaches what will become Earth. Both objects have been growing in similar orbits, occasionally coming close to one another, but not yet colliding. Their paths influenced by the gravity of the other planetesimals and protoplanets scattered through the inner system. Their orbits gradually become more similar through gravitational interactions, bringing them closer together with each orbit, until a collision becomes likely. The timing of this encounter is somewhat random, dependent on the specific configuration of all the objects in this region, but the outcome is almost certain, given enough time. When Theia finally impacts the proto-Earth, the collision ranks among the most violent events in Earth's history. An impact between two planetary mass bodies traveling at several kilometers per second relative to one another. The collision occurs at an oblique angle, not head-on, which determines what happens next. The impact vaporizes a substantial portion of both objects' mantles, creating a cloud of rock vapor that spreads around Earth in a disk. The cores of both bodies merge in the collision, adding Theia's iron to Earth's core and establishing much of the final mass our planet will have. The debris from this impact, rock vapor and molten material thrown into orbit around Earth, begins to cool and condense over the following centuries and millennia. This debris disk orbiting Earth behaves like a miniature version of the solar disk itself, with material colliding and sticking together to form larger bodies. Over perhaps 10,000 to 100,000 years, this debris accumulates into a single large satellite orbiting Earth, which we now call the Moon. The Moon forms close to Earth, perhaps only 20,000 kilometers away, compared to the nearly 400,000 kilometers separating them today, appearing enormous in Earth's sky and raising massive tides in the molten rock of Earth's surface. Similar collisions shape the formation of all the inner planets, though not all produce large moons like Earth's. Mercury forms closest to the Sun, where temperatures are highest and available material is scarcest, becoming the smallest of the rocky planets, less than half Earth's diameter. Venus forms at a similar distance from the Sun as Earth will orbit, growing to almost exactly Earth's size, but without experiencing a moon-forming collision like Earth's. Mars forms farther out, where material density is lower, resulting in a planet about half Earth's diameter with less than a tenth of Earth's mass, too small to hold on to a thick atmosphere against the solar wind. The inner disk gradually clears as planets accrete most of the available material, sweeping their orbital zones clean through direct impacts and gravitational interactions. The timescale for this clearing is tens of millions of years, with most of the mass being incorporated into planets within about 50 million years of the Sun's formation. What remains after the planets form includes countless smaller bodies that were not swept up, asteroids that will eventually populate the main asteroid belt between Mars and Jupiter, prevented from forming a planet by Jupiter's gravitational interference. We watch as the young rocky planets slowly cool from their molten birth states, their surfaces solidifying into crusts that are immediately shattered by continued bombardment from remaining planetesimals. No stable surface can yet form because impacts continue at a high rate, each large collision melting the crust in the impact region, and sometimes globally. The planets remain hellish by human standards, airless or with only thin atmospheres of rock vapor, their surfaces glowing with heat, continually reshaped by violence from space. The solar wind continues to blast through the inner system, stripping away any hydrogen and helium that the small rocky planets might temporarily capture from the surrounding disk. These light elements cannot be held by the weak gravity of bodies this small, especially not when the sun's energy continually pushes them away. The rocky planets will have to form their later atmospheres through outgassing from their interiors and possibly from volatile materials delivered by comets and asteroids from the outer solar system, a process that will take millions of years and occur only after the bombardment phase decreases. As the disk gas dissipates over the first few million years after the sun's formation, cleared away by solar wind and radiation pressure, and by accretion onto the star and planets, the era of rapid planet formation in the inner system comes to an end. The planets have reached nearly their final masses, with only modest additional growth coming from the remaining debris that will continue to strike them for millions of years to come. The inner solar system has established its basic architecture: 4 rocky worlds orbiting within the warm inner region, separated by millions of kilometers, but all bathed in light from the same central star. Beyond the orbit of Mars, beyond the rocky realm we have been observing, conditions are different enough to produce an entirely different class of worlds. And it is toward that colder region, where ice dominates, that our journey continues. Our spacecraft moves outward through the solar disk, crossing the boundary where temperature drops enough for water ice to condense as solid frost on the surfaces of dust grains. This invisible line, the frost line or snow line, sits roughly 3 to 5 astronomical units from the Sun, beyond the orbit that Mars will eventually settle into. Crossing this threshold changes everything about planet formation, transforming the process from one limited by scarce rocky material to one where abundant ice allows objects to grow far larger than anything possible in the inner system. The difference becomes immediately visible through our viewing ports as we drift into the colder region, with ice-coated grains outnumbering bare rock by a significant margin. Water is abundant in the universe, oxygen being the 3rd most common element after hydrogen and helium, and wherever temperatures allow, water freezes into ice that can participate in building solid worlds. Beyond the frost line, the total amount of solid material available for planet formation increases by a factor of several times compared to the inner disk, simply because ice adds so much mass to what would otherwise be only small, rocky, and metallic grains. This abundance of building material means planetesimals can grow larger here and grow faster, accumulating ice and rock together into bodies with much more mass than their counterparts closer to the Sun. The icy planetesimals stick together effectively when they collide, the ice-creating surfaces that adhere readily when they touch at the low speeds typical of encounters between objects in similar orbits. Over time, the largest bodies in this region sweep up material from wide zones around their orbits, growing to masses of several Earth masses, while the inner planets are still assembling themselves from smaller protoplanets. The key to forming gas giant planets lies in growing a solid core massive enough to gravitationally capture and hold on to the hydrogen and helium gas still present in the disk. This requires reaching the critical core mass of roughly 10 Earth masses, the threshold at which a body's gravity becomes strong enough to pull in significant amounts of light elements from the surrounding nebula. In the inner system, this threshold cannot be reached because insufficient solid material exists. But beyond the frost line, where ice abounds, cores can grow large enough to cross this crucial boundary. We watch as Jupiter's core forms in the region about 5 astronomical units from the Sun, a massive accumulation of ice and rock that grows rapidly by the standards of planet formation, reaching 10 Earth masses within perhaps 2 to 3 million years of the disk's formation. Once the core crosses the critical mass threshold, the surrounding hydrogen and helium begin falling onto it, initially slowly, but with accelerating pace as the planet's mass increases. The growing gravity attracts more gas, which increases the mass, which strengthens the gravity further, creating another runaway process that ends only when the local disk is cleared of available material. Jupiter's growth happens fast on cosmic timescales, with most of the gas accretion occurring over perhaps 1 million years, building the planet to the enormous size we see today, more than 300 times Earth's mass and over 11 times Earth's diameter. The planet becomes the dominant object in the solar system, aside from the Sun itself, containing more mass than all other planets combined, a true giant formed from capturing most of the gas in its region of the disk. The final stages of Jupiter's growth may have been limited by the clearing of the disk or by the planet opening a gap in the disk through which less material could flow. Saturn forms farther from the Sun, around 9 astronomical units, where the disk is less dense and the orbital periods are longer, causing everything to proceed more slowly than in Jupiter's region. Saturn's core grows more gradually, taking longer to reach the critical mass needed to accrete significant gas. And by the time it does, the disk has begun to dissipate. Saturn manages to capture a substantial atmosphere, becoming the second largest planet, with about 95 times Earth's mass, but does not grow as large as Jupiter, possibly because the gas supply was depleted or cleared before Saturn could accumulate more. Even farther out, Uranus and Neptune form in the region 10 to 30 astronomical units from the Sun, where the disk is sparser still and orbital times are measured in decades rather than years. These planets grow their cores even more slowly, assembling ice and rock over longer timescales in a region where material is spread across vast volumes of space. Their cores may reach the critical mass for gas accretion, but by the time they do, most of the hydrogen and helium has already been cleared from the disk by solar wind or incorporated into Jupiter and Saturn. Uranus and Neptune end up as ice giants rather than gas giants, with masses of about 15 and 17 Earth masses, respectively, much smaller than Jupiter and Saturn. Their composition differs significantly from their larger siblings, with a greater proportion of ice and rock and smaller atmospheres of hydrogen and helium. Scientists sometimes classify them separately as ice giants to distinguish them from the true gas giants Jupiter and Saturn, acknowledging that their formation followed a similar path but ended at a different stage. From our position in the outer disk, we observe the complex gravitational interactions between the growing giant planets and the remaining material in the disk. Jupiter's enormous mass creates powerful tidal forces that affect the orbits of nearby planetesimals, preventing them from accumulating into a planet in the region that will become the asteroid belt. Material in certain orbital resonances, with Jupiter experiences repeated gravitational tugs that pump up the eccentricity of their orbits, causing collisions energetic enough to break objects apart, rather than allowing them to merge. The giant planets also interact with each other gravitationally, their orbits slowly evolving as they exchange angular momentum through near resonances and long-range gravitational influences. These interactions can cause the planets to migrate inward or outward from their formation locations, with the direction and magnitude of migration depending on the distribution of remaining disk material and the masses of the planets themselves. Jupiter may have migrated inward somewhat before reversing and moving back outward, a process that would have dramatically affected the distribution of material throughout the solar system. Saturn's formation and subsequent migration potentially played a crucial role in the final architecture of the outer solar system, with the two largest planets possibly moving into and then out of certain orbital resonances with each other. These resonances can amplify the migration effects, causing more rapid changes in orbital distances and potentially scattering smaller bodies throughout the system. The gravitational dance between Jupiter and Saturn may have determined the final positions of Uranus and Neptune and shaped the distribution of small bodies in the outer solar system. We witness streams of gas flowing onto the growing Jupiter, material spiraling down from the surrounding disk toward the planet's surface like water circling a drain. The planet grows hot from this accretion, the gravitational energy of infalling material converting to heat and making the young Jupiter glow in infrared light far more brightly than it does today. The planet may shine almost like a faint star in this phase, its luminosity coming from contraction and accretion rather than from fusion, which never occurs because the planet's mass remains far below the threshold needed to ignite hydrogen. Around Jupiter and the other giant planets, smaller disks of material orbit the forming worlds, circumplanetary disks similar to the solar disk, but scaled down in size. Within these mini-disks, moons begin to form through the same processes of collision and accretion that built the planets themselves. The large, regular moons of Jupiter, the 4 satellites Galileo would later discover with his telescope, form from material in Jupiter's circumplanetary disk, orbiting in the planet's equatorial plane in nearly circular orbits. The giant planets create a different environment in the outer solar system compared to the rocky planets of the inner system, their powerful gravity influencing vast regions of space around them. Their formation represents a one-time opportunity that closes when the disk gas disperses, after which gas giants cannot form because the light elements are no longer available. The presence or absence of giant planets in a planetary system depends critically on timing, on whether cores can grow large enough before the gas is cleared, making gas giants somewhat rarer than rocky planets around other stars. As we observe the giant planets settling into their orbits, their atmospheres still evolving as material continues to fall onto them from the dispersing disk, we see the outer solar system taking shape. Beyond Neptune, the disk extends outward into a vast region where temperatures remain near absolute zero and where countless small icy bodies orbit in the cold darkness. This region will become the source of comets that occasionally fall inward to visit the inner system. But for now, it remains largely undisturbed, a frozen reservoir of pristine material from the solar system's formation. We drift forward through time, our spacecraft now observing the solar system roughly 500 million years after its formation, a period when the architecture seems nearly established, but when the system remains far more chaotic than the calm configuration we know from billions of years later. The planets exist in their approximate orbital positions, but something is about to change, a period of upheaval that will reshape surfaces throughout the inner system and scatter debris from the outer reaches. Scientists who study this era call it the late heavy bombardment, a time when impact rates spike dramatically across the inner solar system. The trigger for this bombardment appears to be a gravitational instability in the outer solar system, likely involving the orbits of Jupiter, Saturn, Uranus, and Neptune. The giant planets have been slowly migrating since their formation, their orbits evolving as they interact with the remaining disk material and with each other through long-range gravitational influences. These migrations proceeded gradually at first, but when certain orbital relationships form between the planets, resonances can develop that dramatically amplify the interaction strengths and cause more rapid changes. The leading model for what happens, developed by scientists studying orbital dynamics and backed by computer simulations, suggests that Jupiter and Saturn move into a 2-to-1 orbital resonance, where Saturn completes exactly one orbit for every 2 Jupiter completes. This resonance creates a regular repeating gravitational tug between the two planets that builds over time, pumping energy into Saturn's orbit and causing both planets' orbits to become more eccentric and to migrate, Jupiter inward and Saturn outward from their initial positions. This migration of the giant planets proves catastrophic for the small bodies in the outer solar system, particularly those orbiting in the region beyond Neptune, where billions of icy planetesimals remain from the formation era. As Neptune migrates outward, its gravity sweeps through this population, scattering objects in all directions, sending some into the inner solar system, some into highly elliptical orbits, and others out of the solar system entirely. The orbital changes happen over perhaps a few 100,000 years, rapid by astronomical standards, but still spanning more time than human civilization will eventually exist. From our vantage point in the outer system, we watch as Neptune's orbit expands outward, the planet plowing through the swarm of icy bodies like a gravitational bulldozer, clearing a path. Objects that come near Neptune experience powerful gravitational encounters that fling them onto new trajectories. Their orbits transformed from nearly circular paths into elongated ellipses that carry them throughout the solar system. Some objects are thrown inward toward the sun, beginning long falls that will end in collisions with planets, or in close passes by the sun that either destroy them or send them back outward. Uranus experiences similar orbital evolution, also scattering planetesimals as it migrates, adding to the chaos spreading through the outer system. The two ice giants may have even switched positions, with the planet that formed closer to the Sun ending up farther out, though this remains uncertain based on current models. What is clear from the evidence is that the outer planets did not form in their current locations, but migrated there. And this migration scattered a vast population of small bodies throughout the system. The scattered planetesimals include objects of all sizes, from tiny ice particles to bodies hundreds of kilometers across, each one a pristine sample of material from the solar system's formation. Those sent inward cross the orbits of the inner planets, and the chances of collision increase dramatically, with so many objects on chaotic paths through the inner system. Earth, Moon, Mars, Venus, and Mercury all experience a surge in impact rates, their surfaces bombarded by asteroids and comets, arriving from the outer reaches at high velocities. We position our spacecraft in orbit around Earth to witness the bombardment as it intensifies, watching from a safe distance as impact after impact strikes the surface below. The Earth at this time has cooled significantly from its molten birth, developing a solid crust and perhaps early oceans, though conditions remain harsh by later standards. Each large impact temporarily reverses this cooling, melting rock at the impact site, and sometimes globally, vaporizing any surface water in the region and ejecting debris into orbit that eventually falls back as a rain of molten rock. The Moon receives its share of the bombardment as well, with large impacts creating the vast circular basins we see today as the Dark Maria, or seas on its surface. The largest impacts excavate craters hundreds of kilometers across, their ejecta spreading across the lunar surface in rays that extend for thousands of kilometers. The Imbrium Basin, Serenitatis, Chrysium, and others all formed during this period, their floors later filled with dark basaltic lava that erupted from the lunar interior to create the smooth plains visible from Earth. Mars experiences bombardment that reshapes its southern highlands, creating dense concentrations of overlapping craters that remain visible billions of years later as testimony to this violent era. The impacts deliver energy that heats the Martian crust, possibly triggering volcanic activity and affecting the planet's early climate. Some scientists suggest the bombardment may have delivered significant amounts of water to Mars, though much of this water would later be lost to space or frozen into the subsurface as the planet's atmosphere thinned. Venus and Mercury also bear the scars of bombardment, though on Venus later volcanic activity has erased most of the evidence by resurfacing the planet. And Mercury's heavily cratered appearance testifies to impacts from both the formation era and the later bombardment. The inner solar system becomes a dangerous place during this period, with large impacts occurring every few thousand years on Earth, and more frequently on smaller bodies, each strike releasing energy equivalent to millions or billions of nuclear weapons, depending on the impactor's size. The bombardment gradually declines as the supply of scattered objects is depleted, with most planetesimals either colliding with something, being ejected from the solar system, or settling into stable orbits where they no longer threaten the planets. The timescale for this decline is roughly 100 million years, with impact rates dropping from the peak back down to the much lower background rate that will persist for billions of years afterward. By about 3.8 billion years ago, approximately 800 million years after the solar system's formation. The bombardment has largely ended, and the system achieves a more stable configuration. Evidence for the late heavy bombardment comes from multiple sources, including the ages of rocks returned from the moon by Apollo astronauts, which show a clustering of impact melt ages around 3.9 billion years ago. Crater densities on ancient surfaces throughout the solar system also suggest a period of higher impact rates in this time frame. However, some scientists debate the details, questioning whether the bombardment was a distinct event or simply the tail end of the formation process, with impacts declining smoothly from earlier times. We observe the outer solar system as the chaos subsides, watching Neptune and Uranus settle into their final orbits and the scattered disk population thin dramatically from its initial density. The region beyond Neptune, now called the Kuiper Belt, retains a population of icy bodies that escaped being scattered. Objects in orbits that Neptune's migration swept into stable resonances rather than ejecting. These bodies will remain there for billions of years, a frozen archive of material from the solar system's formation. Some scattered objects end up in a vast spherical cloud surrounding the solar system, at distances of thousands to tens of thousands of astronomical units, far beyond the planets, barely bound to the sun by gravity. This cloud, later named the Oort cloud, after the astronomer who predicted its existence, serves as the source region for long-period comets that occasionally have their orbits perturbed by passing stars or galactic tides, sending them falling inward to pass through the inner system. The giant planets have achieved their final configuration, with Jupiter at 5.2 astronomical units, Saturn at 9.5, Uranus at 19, and Neptune at 30, orbits that will remain stable for billions of years to come. Their migration and the resonances they created have shaped the entire solar system's structure, determining the distribution of asteroids, the population of Kuiper Belt objects, and possibly affecting the delivery of water and organic materials to Earth during the bombardment. As the impact rates decline and the solar system enters a calmer phase, the stage is set for the long era of stability that will allow surfaces to cool, atmospheres to develop, and on at least one planet, the chemistry of life to begin. The violence of formation and bombardment has ended, and the solar system as we know it begins to emerge from the chaos. Our spacecraft moves through the inner solar system as it exists today, roughly 4.5 billion years after formation, and billions of years into the stable configuration achieved after the bombardment era ended. The region between the Sun and the asteroid belt contains 4 worlds of rock and metal, each one distinct in character and condition, shaped by their formation histories and by their positions relative to the Sun. We begin our observation closest to the central star, where Mercury orbits in the intense light and heat that define existence in the innermost zone. Mercury circles the Sun at an average distance of just under 60 million kilometers, roughly 4/10 of an astronomical unit, completing each orbit in only 88 Earth days. The planet is small, barely larger than Earth's moon, with a diameter of about 4,800 kilometers and a mass only 6% that of Earth. From our spacecraft in orbit around Mercury, the Sun appears more than 3 times larger than it does from Earth, dominating the sky and delivering 11 times more energy per square meter to the planet's surface than Earth receives. The surface below us shows heavy cratering from billions of years of impacts, the scars from the formation era and bombardment period, preserved in ancient terrain that covers much of the planet. The largest feature visible is the Caloris Basin, an impact structure over 1,500 kilometers across, created when an asteroid struck Mercury with tremendous force, sending shockwaves through the entire planet. The impact was energetic enough to create disrupted terrain on the opposite side of Mercury, where seismic waves from the impact focused and fractured the surface. Mercury's surface temperature varies more extremely than any other planet's, ranging from over 400 degrees Celsius in sunlight to below minus 180 degrees Celsius in shadow, a swing of nearly 600 degrees between day and night. This enormous variation occurs because Mercury has essentially no atmosphere to redistribute heat. Only an extremely thin exosphere of atoms temporarily knocked off the surface by solar wind impacts. Without atmospheric insulation, heat absorbed during the long day radiates away immediately on the night side, allowing temperatures to plummet despite the planet's proximity to the Sun. We observe Mercury's slow rotation, one of the unusual characteristics that distinguish this world from most other planets. Mercury rotates on its axis exactly 3 times for every 2 orbits around the Sun, a 3-to-2 spin-orbit resonance that arose from tidal interactions between the planet and the Sun over billions of years. This resonance means that Mercury's day, from one noon to the next noon at a given location, lasts 176 Earth days, 2 full Mercury years. The long days and nights contribute to the extreme temperature variations, with surfaces baking in sunlight for 88 Earth days before rotating into 88 days of darkness. Beneath the heavily cratered surface lies an unusually large metallic core, making up perhaps 60 to 70% of Mercury's mass, compared to about 30% for Earth. This enormous core, relative to the planet's size, remains somewhat mysterious, possibly the result of a giant impact early in Mercury's history that stripped away much of the rocky mantle, or possibly due to preferential accretion of metal-rich material close to the Sun. The core generates a weak global magnetic field, surprising for such a small planet, suggesting that at least the outer part of the core remains molten and convecting despite Mercury's small size and age. Moving outward from Mercury, we arrive at Venus, the second planet from the Sun. Orbiting at an average distance of just over 108 million kilometers. Venus is nearly Earth's twin in size, with a diameter of about 12,000 kilometers and a mass 80% of Earth's, formed from similar materials in a similar region of the early solar disk. But the similarity ends with size and composition, because Venus has evolved into a world radically different from Earth, hidden beneath clouds that never part and hostile to any surface exploration. The atmosphere of Venus is thick beyond comparison with Earth, exerting a surface pressure 90 times greater than Earth's atmosphere, equivalent to the pressure 1 kilometer deep in Earth's oceans. This dense atmosphere consists of 96% carbon dioxide, with clouds of sulfuric acid droplets suspended in layers above the surface, creating a greenhouse effect so extreme that surface temperatures reach 470 degrees Celsius, hot enough to melt lead. The clouds completely hide the surface from visible light observation, making Venus appear as a featureless white sphere when viewed from space. Through radar imaging from orbiting spacecraft, we can peer through the clouds to map the surface below, revealing a landscape dominated by volcanic features, vast plains of solidified lava, and highland regions that may be older crust. Venus shows evidence of extensive volcanic activity, possibly ongoing, with thousands of volcanic structures scattered across the surface, ranging from small cones to enormous shield volcanoes, larger than any on Earth. The entire surface appears relatively young in geological terms, perhaps only 500 million years old, suggesting that a global resurfacing event may have covered older terrain with fresh lava. Venus rotates incredibly slowly and in the opposite direction from most planets, turning once every 243 Earth days in a retrograde direction, meaning the Sun rises in the west and sets in the east. The reason for this backward rotation remains debated, possibly the result of a massive impact that tipped the planet over early in its history, or possibly due to complex atmospheric tidal interactions with the Sun over billions of years. The slow rotation, combined with a thick atmosphere, creates unusual circulation patterns, with winds at cloud level reaching hundreds of kilometers per hour, even though surface winds are nearly calm. We continue outward to Earth, the third planet, orbiting at 1 astronomical unit from the Sun, 150 million kilometers, on average. Earth appears as a blue and white marble from space, the only planet in the solar system with liquid water oceans covering most of its surface, the only world known to harbor life. Continents of lighter-colored rock break the blue expanse, their shapes familiar from maps and satellite images, surrounded by the deep ocean basins that hold the vast majority of Earth's surface water. Earth's atmosphere is transparent invisible light, thin compared to Venus, but substantial enough to moderate temperatures and protect the surface from harmful radiation. Nitrogen and oxygen dominate the atmospheric composition, with the oxygen primarily a product of billions of years of photosynthesis by living organisms, making Earth's atmosphere unique in the solar system. Clouds of water vapor drift through the atmosphere, forming and dissipating in patterns driven by the planet's weather systems, themselves powered by solar heating and Earth's relatively rapid rotation. The surface shows remarkable variety from our orbital vantage point, with different climates and environments visible across the planet's latitude zones. Ice caps cover both poles, white expanses of frozen water extending thousands of kilometers from each pole toward the equator, where warmth melts the ice. Between the ice and the tropics lie temperate regions, where seasons change as Earth's tilted axis causes different hemispheres to receive more or less direct sunlight through the year. The tropics themselves show green vegetation, where rain falls, and brown deserts where it does not. The distribution of water determining which regions support abundant life. Earth's moon orbits at an average distance of 384,000 kilometers, appearing as a grey cratered sphere about 1/4 Earth's diameter. The moon remains tidally locked to Earth, showing the same face toward Earth at all times, a result of gravitational interactions that synchronized its rotation with its orbital period over billions of years. From the moon's surface, Earth would appear suspended, nearly motionless in the sky, slowly showing different faces as Earth rotates, but never rising or setting, a view only a few human beings have actually witnessed firsthand. Moving outward past Earth, we reach Mars, the fourth and final rocky planet, orbiting at an average distance of about 228 million kilometers from the Sun. Mars appears distinctly reddish from space, the color coming from iron oxide minerals, essentially rust, coating much of the planet's surface. The planet is roughly half Earth's diameter and has only about 10% Earth's mass, a smaller world that cooled more quickly and lost much of whatever atmosphere it may have initially possessed. The Martian surface shows features from different eras of the planet's history, with heavily cratered southern highlands dating back billions of years, and smoother northern plains that may have once held an ocean of liquid water. Enormous volcanoes rise in the Tharsis region, including Olympus Mons, the largest volcano in the solar system, towering 25 kilometers above the surrounding plains. A vast canyon system, Valles Marineris, stretches across nearly a quarter of the planet's circumference, dwarfing Earth's Grand Canyon in both length and depth. Evidence of ancient water is visible throughout the Martian landscape, with dry river valleys, lake beds, and mineral deposits that form only in the presence of liquid water. Mars once had a thicker atmosphere and warmer climate that allowed water to flow across its surface, but the planet's small size meant it could not hold on to this atmosphere indefinitely. The lack of a global magnetic field allowed solar wind to gradually strip away the atmosphere over billions of years, and as the atmosphere thinned, the water froze or evaporated, leaving Mars the cold, dry desert world we observe today. Between Mars and Jupiter lies the asteroid belt, a region containing millions of rocky and metallic bodies, ranging from tiny particles to objects hundreds of kilometers across. These asteroids represent material that never accumulated into a planet, prevented from doing so by Jupiter's gravity, stirring the region and causing collisions too energetic for accretion. The largest asteroid, Ceres, is big enough that its own gravity has pulled it into a roughly spherical shape. But most asteroids are irregular chunks of rock and metal, remnants from the solar system's formation that continue to orbit the Sun in this intermediate zone. Beyond the asteroid belt, our spacecraft crosses into the outer solar system, where the giant planets dominate. Worlds so different from the rocky inner planets that they seem to belong to a separate category of objects altogether. We approach Jupiter first, the largest planet in the solar system, orbiting the Sun at an average distance of about 778 million kilometers, just over 5 astronomical units. Even from millions of kilometers away, the planet's immense size becomes apparent. A vast sphere, more than 11 times Earth's diameter, and more than 300 times Earth's mass. Jupiter is composed primarily of hydrogen and helium, the lightest elements, giving it a low average density despite its enormous mass, less than 1.5 times the density of water. The planet has no solid surface in the conventional sense, instead transitioning gradually from a thin outer atmosphere through layers of increasing pressure and density until hydrogen becomes liquid, then metallic, surrounding a possible core of rock and ice at the center. The atmosphere we see from outside represents only the outermost layer of a planet that extends tens of thousands of kilometers deep. The visible atmosphere shows striking patterns of light and dark bands parallel to the equator, regions of different temperature and composition organized by the planet's rapid rotation and powerful winds. Jupiter rotates faster than any other planet, despite its size, completing one rotation in less than 10 hours, which creates strong Coriolis forces that organize atmospheric circulation into these distinct zones. and belts. Light-colored zones are regions of upwelling gas, while darker belts are areas of sinking material, the whole pattern driven by internal heat rising from the planet's interior and by absorbed sunlight. The Great Red Spot, visible as an enormous oval feature in the southern hemisphere, represents a storm system larger than Earth, a high-pressure region that has persisted for at least several centuries, and possibly much longer. Winds in the Great Red Spot circulate counterclockwise at speeds exceeding 400 kilometers per hour, driven by temperature differences and by the rotation of material caught in this long-lived atmospheric feature. The spot's red color may come from complex organic molecules created by solar ultraviolet radiation, acting on simpler compounds brought up from deeper in the atmosphere. From our spacecraft, we observe Jupiter's extensive moon system, with the 4 large moons discovered by Galileo visible even through small telescopes from Earth. Io, the innermost of the 4, appears distinctly orange and yellow, the most volcanically active body in the solar system, with eruptions constantly resurfacing the moon and preventing any impact craters from accumulating. Io's volcanism is driven by tidal heating, the gravitational pulls of Jupiter and the other moons flexing Io's interior and generating tremendous heat through friction. Europa, the second Galilean moon, shows a surface of water ice, crisscrossed by dark linear features that may be cracks in an ice shell covering a liquid water ocean beneath. The relatively smooth surface lacks large craters, suggesting recent or ongoing resurfacing by ice rising from below or by the freezing of liquid water that reaches the surface. Europa's subsurface ocean, if it exists, as most scientists believe, could contain more liquid water than all of Earth's oceans combined, maintained in liquid form by tidal heating, similar to what affects Io. Ganymede, the largest moon in the solar system, exceeds the planet Mercury in diameter, though not in mass, with a surface showing both dark ancient terrain and lighter grooved regions formed more recently. Ganymede possesses its own magnetic field, the only moon known to have one, generated by motions in a liquid iron core, or possibly in a salty ocean beneath the ice. Callisto, the outermost Galilean moon, shows the most heavily cratered surface, ancient terrain that has changed little over billions of years, suggesting less internal activity than the other 3 large moons. Dozens of smaller moons orbit Jupiter at various distances, some close to the planet, moving among the faint rings that circle Jupiter's equator, others far out in irregular orbits that suggest they were captured asteroids or comets rather than forming with Jupiter. The entire system resembles a miniature solar system, with Jupiter as the central body, the moons following the same gravitational laws that govern planets around the Sun. Moving outward from Jupiter, we reach Saturn at an average distance of about 1.4 billion kilometers from the Sun, 9.5 astronomical units. Saturn rivals Jupiter in size, with a diameter more than 9 times Earth's, but contains less mass, only about 95 Earth masses, giving it the lowest average density of any planet, less than the density of water. Like Jupiter, Saturn consists mostly of hydrogen and helium with no solid surface. And like Jupiter, Saturn rotates rapidly, completing one rotation in about 10.5 hours. Saturn's atmosphere shows banded structure similar to Jupiter's, though with more muted colors, tan and pale yellow predominating, with occasional white storm systems appearing in certain latitudes. The planet occasionally develops large storms that wrap around its equator. Outbreaks of convection from deeper layers that create bright white features, visible even from Earth. Saturn's winds are among the fastest in the solar system, reaching 1,500 kilometers per hour in the equatorial regions, faster than Jupiter's, despite Saturn receiving less solar energy. The defining feature of Saturn, visible even through small telescopes from Earth, is the magnificent ring system that circles the planet's equator, extending outward more than twice the planet's radius, while remaining incredibly thin, perhaps only 10 to 30 meters thick in most regions. The rings consist of countless individual particles, mostly water, ice ranging from tiny grains to house-sized chunks, each particle independently orbiting Saturn in a thin disk organized by the planet's gravity and by the gravitational influences of nearby moons. The rings show complex structure when viewed closely, with thousands of individual ringlets separated by gaps and divisions, the most prominent being the Cassini division, a 4,000-kilometer-wide gap visible from Earth. These gaps form through orbital resonances with Saturn's moons, where particles at certain distances orbit in simple ratios relative to a moon's orbit and experience repeating gravitational tugs that clear material from those zones. The rings are relatively young by solar system standards, possibly only a few 100 million years old, perhaps formed from a moon that wandered too close to Saturn and was torn apart by tidal forces. Saturn's moons include Titan, the second largest moon in the solar system, the only moon with a substantial atmosphere, a nitrogen-rich envelope thicker than Earth's atmosphere. Titan's surface remains hidden beneath orange photochemical haze, but radar imaging reveals a landscape with lakes and seas of liquid methane and ethane at the poles, dunes of organic material near the equator, and a possible subsurface ocean of water beneath the icy crust. Titan represents a world with an active hydrological cycle similar to Earth's water cycle, but with methane playing the role that water plays on Earth. Enceladus, a small icy moon only about 500 kilometers in diameter, proved to be one of Saturn's most intriguing moons when spacecraft discovered geysers of water, ice erupting from cracks near its south pole. This moon maintains a subsurface ocean beneath an ice shell, kept liquid by tidal heating from Saturn, and the geysers provide direct samples of that ocean ejected into space. The discovery raised the possibility that Enceladus could harbor life in its ocean, making this small moon a high-priority target for future exploration. Beyond Saturn, the outer solar system grows darker and colder, with the remaining two giant planets receiving only a fraction of the sunlight that illuminates Jupiter and Saturn. We travel outward to Uranus, orbiting at an average distance of about 2.9 billion kilometers, 19 astronomical units, from the Sun. Uranus appears as a pale blue-green sphere, about 4 times Earth's diameter, with a mass roughly 15 times Earth's, making it substantially smaller than Jupiter and Saturn, but still far larger than any rocky planet. Uranus differs from the other giants in composition and in structure, classified as an ice giant rather than a gas giant, because it contains more ice and rock relative to hydrogen and helium. The interior likely consists of a slushy mixture of water, methane and ammonia ices surrounding a rocky core with a relatively thin atmosphere of hydrogen and helium above. The pale blue color comes from methane in the upper atmosphere, which absorbs red light and reflects blue, giving the planet its distinctive hue. The most unusual characteristic of Uranus is its extreme axial tilt, with the planet's rotation axis tipped over 98 degrees from perpendicular to its orbital plane, meaning Uranus essentially rolls along its orbit rather than spinning upright like most planets. This tilt causes each pole to point nearly directly at the Sun at some point during Uranus's 84-year orbit, creating extreme seasons where each pole experiences 42 years of continuous sunlight, followed by 42 years of darkness. The cause of this tilt remains uncertain, possibly the result of a collision with an Earth-sized object early in the planet's history. The final planet in our journey is Neptune, orbiting at an average distance of about 4.5 billion kilometers, 30 astronomical units from the Sun. Neptune appears similar to Uranus in size and composition, slightly smaller in diameter, but slightly more massive, with a similar blue color from atmospheric methane. Despite receiving less solar energy than Uranus, Neptune shows more atmospheric activity, with dark storm systems appearing and disappearing over years, and with the fastest winds measured on any planet, exceeding 2,000 kilometers per hour in some regions. Neptune's largest moon, Triton, orbits in a retrograde direction, opposite to Neptune's rotation, strongly suggesting that Triton was captured by Neptune's gravity rather than forming in orbit around the planet. Triton shows active geology despite its small size and extreme cold, with nitrogen geysers erupting from its surface, driven by seasonal heating of subsurface nitrogen ice by the faint sunlight. Triton's capture likely disrupted any original moon system Neptune may have had, with tidal interactions over time circularizing Triton's orbit, while potentially destroying or ejecting earlier moons. Beyond Neptune, the Kuiper Belt extends outward from about 30 to 50 astronomical units, a region containing thousands of small icy bodies left over from the solar system's formation. Pluto, once considered the 9th planet, orbits in this region along with similar-sized objects, all of them much smaller than the major planets and composed primarily of ice and rock. These Kuiper Belt objects represent pristine samples from the outer solar disk, material that never accumulated into planets, preserved in deep freeze for billions of years. Our spacecraft moves forward through time again, returning to the present era approximately 4.5 billion years after the solar system's formation, settling into observation of the Sun as it exists today in what astronomers call its main sequence phase. The Sun appears much as it has for billions of years, and much as it will continue to appear for billions more, a yellow star of spectral type G2, burning steadily through nuclear fusion in its core, maintaining the balance between gravity and pressure that defines a stable star. At the Sun's center, temperatures exceed 15 million degrees Kelvin, and pressures reach more than 200 billion times Earth's atmospheric pressure. Conditions extreme enough to force hydrogen nuclei together, despite their electrical repulsion. 4 hydrogen nuclei, protons, combine through a series of steps to form one helium nucleus with a small amount of mass, converting to energy in the process. This fusion occurs at a rate of about 600 million tons of hydrogen every second. Yet the Sun contains enough fuel to maintain this rate for approximately another 5 billion years before exhausting the hydrogen in its core. The energy created by fusion emerges as high-energy gamma-ray photons that immediately collide with surrounding particles, beginning a long journey outward through the Sun's interior. The core region where fusion occurs extends to about 25% of the Sun's radius, containing about half the Sun's mass. And any photon created there must pass through all the layers above before reaching the surface. The photons scatter endlessly between particles, absorbed and re-emitted countless times, each interaction changing their direction randomly in a process that takes tens of thousands to hundreds of thousands of years to carry energy from core to surface. Above the core lies the radiative zone, extending to about 70% of the Sun's radius, where energy moves outward primarily through radiation. Photons hopping from particle to particle in their slow, random walk toward lower density regions. The temperature and pressure decrease with increasing distance from the core, dropping to about 2 million degrees at the top of the radiative zone. Above this lies the convective zone, where energy transport changes from radiation to convection, with hot plasma rising to the surface, cooling and releasing its energy, then sinking back down to be reheated in a continuous circulation. From our distant vantage point, we observe the Sun's visible surface, the photosphere, a layer a few hundred kilometers thick from which most of the light we see escapes into space. The photosphere's temperature measures about 5,700 degrees Kelvin, hot enough to glow yellow-white, and its features include granulation, a cellular pattern created by convection cells bringing heat from below. Each granule represents the top of a rising column of hot plasma, surrounded by darker lanes where cooled plasma sinks back down. The whole pattern constantly changing as new granules form and old ones dissipate. Sunspots appear as darker regions on the photosphere, areas where strong magnetic fields suppress convection and reduce the temperature relative to surrounding areas. These spots appear dark only by contrast, still glowing at temperatures of about 4,000 degrees Kelvin, but appearing darker against the brighter 5,700 degree background. Sunspot numbers vary in an 11-year cycle driven by the Sun's magnetic field, which strengthens, twists, and reconnects in patterns that create more or fewer spots depending on where the Sun is in the cycle. Above the photosphere lies the chromosphere, a thin layer visible during solar eclipses as a reddish glow around the Sun's edge, and above that extends the corona, the Sun's outer atmosphere of extremely hot but very tenuous plasma, reaching millions of degrees Kelvin. The corona extends millions of kilometers into space, gradually transitioning into the solar wind, a constant outflow of charged particles, mostly electrons and protons, that stream away from the Sun in all directions at hundreds of kilometers per second. The solar wind fills the solar system, flowing outward past all the planets, creating the heliosphere, a bubble of solar influence that extends well beyond the orbit of Neptune. The wind interacts with planetary magnetic fields where they exist, compressing them on the sunward side and stretching them into long tails on the night side. For planets with atmospheres but weak or no magnetic fields, like Mars and Venus, the solar wind gradually strips away atmospheric particles over geological time, one factor in Mars's atmospheric loss over billions of years. The Sun has been in this stable main sequence configuration for about 4.5 billion years, Halfway through the approximately 10 billion year lifetime, a star of its mass spends fusing hydrogen in its core. During this time, the Sun has gradually brightened as helium accumulates in the core and increases the density and temperature there, causing fusion rates to increase slowly. When the Sun first reached the main sequence, it was about 70% of its current brightness, and it continues to brighten by about 10% every billion years. A gradual change with profound implications for Earth's climate over geological time. Earth's climate has remained suitable for liquid water on the surface throughout most of its history, despite the Sun's increasing brightness. A situation sometimes called the faint young sun paradox. Early Earth likely had higher concentrations of greenhouse gases in its atmosphere, warming the planet enough to maintain liquid water despite receiving less solar energy. As the Sun brightened over billions of years, geological and biological processes reduced atmospheric greenhouse gas concentrations, maintaining roughly stable temperatures through a balance between increasing solar output and decreasing atmospheric warming. The Sun's current stable state represents a balance of enormous forces, with gravity pulling inward on every particle of solar material, trying to compress the Sun to smaller size, while pressure from the heat generated by fusion pushes outward with exactly the right force to prevent collapse. This balance, called hydrostatic equilibrium, remains stable as long as fusion continues in the core, because fusion automatically adjusts its rate in response to changes in temperature and pressure, creating a self-regulating system. If the Sun's core temperature were to increase for any reason, the fusion rate would increase, producing more energy, which would increase the pressure, causing the Sun to expand slightly, which would cool the core and reduce the fusion rate back to equilibrium. Similarly, if the core cooled, fusion would slow, pressure would decrease, the Sun would contract slightly, heating would increase, and fusion would speed back up. This thermostatic control maintains the Sun's stability over billions of years, allowing stars like the Sun to burn steadily for enormous lengths of time. We observe the Sun from Earth's orbit, watching its steady light illuminate the planets, power Earth's weather and climate, enable photosynthesis and life, and define the conditions throughout the solar system. The Sun contains 99.8% of all the mass in the solar system, dominating everything gravitationally and energetically. The planets, moons, asteroids, and comets collectively amount to a rounding error in mass compared to the Sun. Yet they owe their existence and their characteristics to this central star and to the processes that formed it. The Sun's stability over billions of years has allowed the solar system structure to persist largely unchanged since the bombardment era ended, with planetary orbits remaining predictable and stable through countless revolutions. Jupiter has orbited the Sun roughly 370 million times since the solar system formed. Earth nearly 4.5 billion times, each orbit following the same elliptical path, shaped by the balance between orbital velocity and solar gravity, a balance that has held for eons. Looking ahead, the Sun will continue in this stable state for approximately another 5 billion years, with conditions changing only gradually as the helium content in the core slowly increases. Life on Earth, if it continues that long, will have to adapt to a slowly brightening Sun, with Earth potentially becoming too hot for liquid water on the surface in perhaps 1 to 2 billion years. as solar output increases beyond what geological processes can compensate for, through reducing atmospheric greenhouse gases. The main sequence phase represents the prime of a star's life, the period when it burns most efficiently and stably, when it provides the consistent energy needed to support complex chemistry and potentially life on orbiting worlds. Stars spend a substantial fraction of their total lifetimes in this phase, with more massive stars progressing through it faster and lower mass stars taking far longer. Our Sun, as a medium mass star, enjoys a lengthy main sequence lifetime that allows ample time for planets to cool, life to emerge and evolve, and complex systems to develop. From our perspective in the present, 4.5 billion years into the Sun's life, and roughly the same amount of time remaining before major changes begin, the solar system feels eternal. The Sun appears unchanging, and the rhythms of planetary orbits seem as permanent as anything in the universe. But this sense of permanence is an illusion created by human timescales, brief flickers compared to stellar lifetimes, and deep within the Sun's core, the hydrogen fuel is slowly but inevitably being consumed. We accelerate forward through time in our spacecraft, moving billions of years into the future, approaching the era roughly 5 billion years from now, when the Sun will begin to show signs of aging. The hydrogen fuel in the core has been depleting steadily throughout the main sequence, the core's composition shifting gradually from mostly hydrogen to an increasing fraction of helium, the ash of fusion reactions. The fusion zone where hydrogen combines into helium has been slowly moving outward from the very center as the core's hydrogen supply diminishes. In the Sun's deep core, the hydrogen fraction has dropped significantly, with helium now dominating the central region, and this change begins to affect the Sun's structure in noticeable ways. Helium does not fuse at the temperatures and pressures currently present in the core, requiring much more extreme conditions to force helium nuclei together. The helium accumulates inertly in the center, no longer contributing to energy production, while hydrogen fusion continues in a shell surrounding this growing helium core. As the inert helium core grows, it begins to contract under its own weight, no longer supported by the energy production that maintained the Sun's equilibrium during the main sequence. This contraction releases gravitational potential energy, heating the surrounding layers where hydrogen fusion still occurs. The increased temperature in the hydrogen-burning shell causes fusion to proceed more rapidly there, producing more energy than the Sun generated during its main sequence phase. The increased energy output begins to push the Sun's outer layers outward, causing the Sun to slowly swell in size. The transition away from the main sequence happens gradually, over hundreds of millions of years, with the Sun's radius increasing slowly at first, the surface temperature dropping slightly as the photosphere expands, and the same total energy spreads over a larger area. The Sun's color shifts subtly toward orange and red as the surface cools, though the total energy output, the luminosity, actually increases because the larger surface area more than compensates for the lower temperature per unit area. From Earth's orbit, which has remained stable for billions of years, the Sun's changes become increasingly apparent over geological time. The Sun's disk grows perceptibly larger in the sky over millions of years, and the increased luminosity delivers more energy to Earth's surface and atmosphere. Temperatures on Earth begin to rise steadily, slowly at first, but accelerating as the Sun continues to brighten. And this warming proves impossible to counter through geological carbon cycle adjustments that worked during the main sequence. Earth's oceans, which have existed for billions of years, begin to evaporate more rapidly as surface temperatures climb above their historical ranges. Water vapor entering the atmosphere creates a runaway greenhouse effect, since water vapor is itself a powerful greenhouse gas, and more warming leads to more evaporation, leads to more warming. Over hundreds of millions of years, Earth's surface temperature rises to levels incompatible with liquid water, the oceans gradually boiling away into the atmosphere and then being lost to space as ultraviolet radiation from the brightening sun breaks water molecules apart in the upper atmosphere. The process of ocean loss is not instantaneous, but extends over geological epochs, with the deepest ocean basins perhaps retaining liquid water for a time, while shallower seas evaporate completely. Eventually, even the deep oceans succumb to the heat, and Earth transitions to a state resembling Venus, with a thick atmosphere of water vapor and carbon dioxide, and surface temperatures hot enough to melt lead. Any life that remained on Earth during this transition faces extinction as habitable environments disappear, ending billions of years of biological evolution. Mars, farther from the Sun, experiences a temporary warming that might seem beneficial if anything remained alive there to benefit from it. The increased solar energy might warm Mars enough to release some of the frozen carbon dioxide and water locked in its polar caps and subsurface, potentially creating a brief period of thicker atmosphere and even liquid water on the surface. But Mars's low gravity means any released atmosphere will eventually be lost to space again, and the warming proves temporary in geological terms. The outer planets and their moons experience more subtle changes, receiving increased energy from the brightening sun, but remaining far enough away that the effects are less catastrophic than for the inner worlds. Europa, Enceladus, and other icy moons with subsurface oceans might experience enhanced internal heating as the sun's energy input increases, though their oceans are maintained primarily by tidal heating rather than by solar energy. Titan's atmospheric chemistry might change as increased ultraviolet and visible light drives different photochemical reactions in its thick atmosphere. The Sun continues its transformation, classified now as a subgiant star, larger and more luminous than a main sequence star, but not yet having reached the dramatic red giant phase. The hydrogen-burning shell around the helium core produces energy more efficiently than core fusion did, causing the Sun's luminosity to increase to several times its main sequence value. The Sun's radius expands to perhaps twice its current size, and the surface temperature drops to around 4,000 to 4,500 degrees Kelvin, giving the Sun a distinctly orange appearance. Inside the Sun, the helium core continues to contract and heat as more helium ash accumulates from the shell, burning above it. The core's temperature climbs toward the 100 million degree threshold required for helium fusion. But at this stage, the core has not yet reached that point. The core exists in a state called electron degeneracy, where matter is compressed so densely that quantum mechanical effects become important. Electrons packed so tightly that further compression becomes extremely difficult regardless of temperature increases. The shell burning proceeds in an unstable manner compared to the steady core burning of the main sequence, with the fusion rate fluctuating and causing the Sun's outer layers to pulsate slightly, expanding and contracting in cycles. These pulsations remain relatively gentle at this stage, but foreshadow the more dramatic variability that will come in later phases. The sun's energy output varies by a few percent over timescales of thousands to millions of years, and the solar wind strengthens, blowing off material from the outer atmosphere at a higher rate than during the main sequence. From our spacecraft, positioned at a safe distance, we watch the sun's gradual transformation, this once stable yellow star becoming something larger, cooler, and more variable. The age of stability has ended, and the sun has entered a phase of accelerating change that will culminate in dramatic transformations over the next several 100 million years. The solar system around this aging star begins to look markedly different from the system that persisted for billions of years during the main sequence. Mercury, closest to the sun, experiences conditions becoming even more extreme as the sun's luminosity increases. Surface temperatures rising far beyond the already extreme values that existed during the main sequence. The day side may reach temperatures that vaporize some of the rock itself, creating a tenuous atmosphere of rock vapor that is immediately blown away by the intensifying solar wind. The planet's surface continues to be bombarded by solar radiation at intensities several times higher than during the sun's stable phase. Venus's thick atmosphere traps even more heat as solar input increases, driving surface temperatures higher still, possibly reaching levels that begin to break down some of the rocks on the surface and altering the chemistry of the atmosphere. The planet's greenhouse effect intensifies beyond even its already extreme state, making Venus even more inhospitable than during the sun's main sequence. The clouds of sulfuric acid may change in composition or altitude as the atmospheric chemistry responds to increased energy input from the enlarging sun. The asteroid belt between Mars and Jupiter receives more warmth than during the billions of years of the main sequence, though remaining far colder than the inner planets. Ice that may have been present on some asteroids might sublimate away, and the increased solar wind pressure could affect the orbits of the smallest particles. Jupiter and the outer giants continue in their orbits, massive enough that the sun's changes barely affect them, though their atmospheres might show subtle changes in temperature and circulation patterns. This subgiant phase represents a transition period, the sun on its way from the stable main sequence to the dramatic red giant phase, but not yet having reached the extreme conditions that will define that later stage. The sun will spend perhaps 1 billion to 2 billion years in this transitional state, gradually expanding and brightening as the helium core grows and contracts, and shell hydrogen burning continues. The pace of change accelerates compared to the glacially slow evolution during the main sequence, but remains slow by human standards, each significant change taking millions of years to manifest. As time continues forward, the helium core's temperature climbs closer to the threshold for helium fusion, approaching 100 million degrees Kelvin. The increasing core temperature raises the temperature of the surrounding hydrogen-burning shell, which increases its fusion rate, which increases the sun's luminosity further, which pushes the outer layers further outward in a feedback process that accelerates the sun's expansion. The next stage of stellar evolution approaches, a transformation that will dramatically change the sun's appearance and the conditions throughout the inner solar system. Moving further forward through time, we reach an era approximately 7 to 8 billion years from now, when the sun's transformation accelerates dramatically into the red giant phase. One of the most striking metamorphoses a star can undergo. The helium core has contracted and heated to the point where helium fusion can finally begin, a process called the helium flash when it occurs in stars of the Sun's mass. This ignition happens suddenly, over just a few seconds after billions of years of contraction, releasing an enormous pulse of energy within the core, though the energy is absorbed by the overlying layers, rather than escaping to make the Sun visibly brighter. The helium flash marks the beginning of the horizontal branch phase for stars of solar mass, where helium, in the core, fuses into carbon and oxygen, while hydrogen continues to burn in a shell around the core. The Sun achieves a new equilibrium, but one very different from the main sequence balance, with the Sun now enormously larger and more luminous than during its stable middle age. The Sun's radius expands to perhaps 100 to 200 times its current size, reaching outward to a distance approaching or possibly exceeding Earth's current orbital radius. From our spacecraft, positioned safely in the outer solar system, we watch the Sun's photosphere expand outward through the inner system, an enormous diffuse sphere of glowing gas stretching across tens of millions of kilometers. The surface temperature drops to around 3,000 to 4,000 degrees Kelvin, cool enough to appear distinctly red or orange, rather than yellow, giving the red giant its name. The Sun's luminosity increases to thousands of times its main sequence value, flooding the solar system with energy despite the cooler surface temperature, the increased surface area compensating for the lower temperature. Mercury, orbiting at an average distance of only 58 million kilometers from the Sun's center, finds itself engulfed as the Sun's photosphere expands beyond its orbit. The planet spirals inward through the outer layers of the Sun's atmosphere, experiencing drag from the tenuous gas that slows its orbital motion. As Mercury loses orbital energy, it falls deeper into the Sun's envelope, the temperature rising rapidly, vaporizing the planet entirely within perhaps a few orbits. The material that was once Mercury mixes into the Sun's outer layers, scattered atoms among the hydrogen and helium. Venus meets a similar fate, its orbit at 108 million kilometers, placing it within, or very near, the maximum extent of the Sun's red giant envelope. Even if Venus avoids direct engulfment, the proximity to the enormously luminous red giant heats the planet to temperatures that vaporize rock, breaking down the very substance of the planet's crust and mantle. The thick atmosphere is blasted away by the intense radiation and the strengthened solar wind, and Venus either falls into the Sun or survives as a scorched remnant, stripped of its atmosphere and perhaps much of its rocky mass. Earth's fate during the red giant phase remains uncertain even in current models, depending on details of the Sun's exact maximum size and on how Earth's orbit evolves as the Sun loses mass through its powerful red giant wind. The Sun will blow off a significant fraction of its mass during this phase, perhaps 25 to 30% of its total, through a stellar wind far stronger than anything during the main sequence. This mass loss causes the Sun's gravitational pull on the planets to weaken, allowing their orbits to expand outward somewhat. Earth's orbit may expand outward to perhaps 1.7 astronomical units as the Sun loses mass, potentially placing Earth just beyond the reach of the Sun's maximum envelope. However, if Earth passes through the outer layers of the Sun's atmosphere at any point, atmospheric drag will cause the orbit to decay, and Earth will spiral inward to destruction. Current models suggest Earth's survival is marginal, with some calculations showing survival and others showing engulfment, depending on assumptions about the Sun's mass loss rate and maximum radius. If Earth survives, it does so as a scorched, lifeless cinder, all atmosphere long since lost, all water gone, the surface heated to temperatures that melt and vaporize rock. The Moon, if it remains bound to Earth, would suffer a similar fate, heated beyond anything a solid body could withstand, while maintaining its structure. More likely, both Earth and Moon are destroyed, falling into the Sun, or being vaporized by the intense heat and broken apart by tidal forces, their material added to the Sun's expanding envelope. Mars, farther from the Sun at roughly 1.5 astronomical units, stands a better chance of survival, likely remaining outside even the maximum extent of the red giant's photosphere. However, Mars receives an enormous increase in solar energy compared to the main sequence era, heating its surface to temperatures far above anything in its earlier history. Any remaining ice in the polar caps or subsurface vaporizes, and the surface may briefly melt before the intense radiation strips away any atmosphere that forms. Mars survives as a scorched remnant in orbit around the dying star, the asteroid belt, positioned between 2.5 and 3.5 astronomical units, experiences intense heating that vaporizes ice and some volatile materials from asteroid surfaces, but likely does not destroy the larger, rocky, and metallic bodies. The asteroids glow from the heat, their surfaces radiating in infrared as they absorb and re-emit the energy from the nearby red giant. Some smaller asteroids may be blown apart by thermal stresses or by the intense solar wind, but the belt as a whole survives in altered form. Jupiter, at 5 astronomical units, finds itself in a very different environment than during the Sun's main sequence, receiving hundreds of times more energy than previously. The giant planet's atmosphere warms significantly, and circulation patterns change in response to the increased heat input. Jupiter's icy moons, including Europa and Ganymede, experience warming that melts their ice shells, potentially creating temporary liquid water oceans on their surfaces. For a brief period, in cosmic terms, perhaps a few million years, these moons might offer conditions suitable for life, warmed by the dying sun's last burst of luminosity. Saturn, Uranus, and Neptune experience similar warming effects, their icy moons temporarily heated above the frozen states they maintained for billions of years. Titan's thick atmosphere warms, possibly driving more active weather, and perhaps creating conditions where liquid water could exist on the surface, alongside the methane lakes. Enceladus, with its subsurface ocean, might see enhanced geyser activity as the ice shell thins and the ocean heats. These outer worlds enjoy a brief spring after billions of years of deep freeze, though this warmth will not last beyond the Sun's red giant phase. The Sun pulsates during the red giant phase, expanding and contracting over periods of thousands to millions of years, the outer layers responding to instabilities in the shell-burning regions. These pulsations grow more dramatic over time, with the Sun eventually entering the asymptotic giant branch phase, where thermal pulses occur periodically, each pulse temporarily increasing the Sun's luminosity and driving strong stellar wind pulses that shed material into space. The Sun becomes highly unstable, its size varying significantly over relatively short timescales. During these pulsations, the Sun ejects its outer envelope into space through a series of powerful winds, creating an expanding shell of gas around the star. This ejected material glows from energy absorbed from the hot core still burning at the center, creating a structure called a planetary nebula, one of the most beautiful phenomena in the galaxy. The nebula expands outward at tens of kilometers per second, carrying perhaps half the Sun's original mass into interstellar space. The nebula expands outward at tens of kilometers per second, carrying perhaps half the Sun's original mass into interstellar space, enriching the galaxy with carbon, nitrogen, oxygen, and other elements created during the Sun's lifetime. From our distant vantage point in the outer system, we watch this expanding shell grow larger over thousands of years, glowing in vivid colors as different elements emit light at characteristic wavelengths. Red from hydrogen, green from oxygen, blue from helium, all mixing together in delicate filaments and structures, shaped by the star's rotation and magnetic fields. This nebula will eventually dissipate over tens of thousands of years, mixing with the interstellar medium, becoming part of future clouds from which future stars might form. The entire red giant phase, including the asymptotic giant branch and the final shedding of the outer layers, lasts approximately 1 billion years from start to finish, though the most dramatic changes occur over the final few million years. Throughout this time, the Sun remains unstable, its appearance changing drastically from decade to decade and century to century, as viewed from the outer planets. What was once a steady yellow star becomes an enormous variable red giant, pulsating and shedding mass, transforming the solar system beyond recognition. Any observer who witnessed the Sun during its long main sequence phase would barely recognize this swollen, unstable, dying star as the same object. As the planetary nebula expands away from the core, what remains at the center gradually becomes visible, no longer hidden beneath the dense outer layers. The core is small, tremendously dense, composed primarily of carbon and oxygen, with a thin outer layer of helium and hydrogen remaining from the incomplete burning. This remnant contains about half to 60% of the Sun's original mass, compressed into a sphere roughly the size of Earth, marking the final transformation from red giant to white dwarf. The ejection of the nebula reveals this hot, dense core, exposing it directly to space for the first time in billions of years. The transition from red giant to white dwarf happens relatively quickly once the envelope is fully shed, taking perhaps only a few tens of thousands of years for the nebula to thin enough that the central star becomes clearly visible. During this brief transition period, the solar system exists in a state between two eras, the expanding nebula still glowing around the newly exposed white dwarf, the surviving planets orbiting through this diffuse glowing gas. The scene carries a strange beauty, destruction and creation mingling in the aftermath of stellar death, the end of one story and the beginning of another unfolding simultaneously. And as the nebula fades into the surrounding space, growing too diffuse to glow any longer, we arrive at the final configuration, the ultimate fate toward which everything has been building since the first moment fusion ignited in the core 7 or 8 billion years ago. The red giant era ends, the instability ceases, and silence returns to what remains of the solar system, a silence that will last far longer than all the previous eras combined. What endures is small, cold, and permanent, stable in a way the Sun never was during its active fusion-burning lifetime. We float, now in the far future, perhaps 10 billion years from the present moment, in a solar system transformed beyond recognition by the passage of time and the death of its star. At the center of the remaining system sits a white dwarf, the remnant core of what was once our Sun. A sphere approximately the size of Earth, containing roughly half of the Sun's original mass, compressed into extraordinary density. The surface glows intensely hot, perhaps 100,000 degrees Kelvin initially, after the outer layers were shed, radiating mostly in ultraviolet wavelengths, invisible to human eyes, but detectable to instruments. This is what remains, the final form, the ember of a star that will cool slowly over trillions of years, but never truly go dark within the current age of the universe. The white dwarf produces no energy through fusion. No hydrogen burns in its core. No helium fuses to carbon. None of the nuclear reactions that powered the Sun throughout its active lifetime. Instead, the white dwarf shines purely from residual heat, leftover thermal energy from the eras of fusion now radiating away into space, with no replenishment. This heat escapes gradually, held in by the immense gravitational field, but inevitably leaking away photon by photon. The white dwarf cooling and dimming over timescales measured in billions of years. The internal structure consists of carbon and oxygen nuclei in a crystalline lattice, surrounded by a degenerate electron gas that provides pressure to resist further gravitational collapse. Electron degeneracy pressure, a quantum mechanical effect arising from the Pauli exclusion principle, prevents the white dwarf from collapsing further under its own gravity. Electrons cannot occupy the same quantum state, and when compressed to the extreme densities present in the white dwarf, they resist further compression with a pressure that does not depend on temperature. This means the white dwarf will remain roughly the same size, regardless of how much it cools, supported by this quantum pressure rather than by thermal pressure, like a normal star. A single teaspoon of white dwarf material, if we could somehow extract it, would weigh several tons on Earth, dense beyond anything found in normal terrestrial experience. From our spacecraft in the outer system, the white dwarf appears as an intensely bright point of light, far smaller than the Sun we remember, but blazingly luminous despite its small size, the high surface temperature compensating for the reduced area. Over time, as we watch across millions and billions of years, the white dwarf gradually dims and shifts color, cooling from blue-white to yellow to orange to red, over incomprehensible spans of time. The cooling follows a predictable curve. Faster initially when the temperature difference between the dwarf and surrounding space is greatest, then slower and slower as the temperature drops. After 10 billion years of cooling, the white dwarf might have a surface temperature around 5,000 degrees Kelvin, similar to the Sun during its main sequence, but its small size would make it far less luminous. The planets that survive the red giant phase continue in their orbits around the white dwarf, though their orbital distances may have increased somewhat due to the mass loss during the giant phases. Jupiter remains, its orbit perhaps slightly expanded to 6 or 7 astronomical units. The giant planet completely frozen, its atmosphere condensed and locked in permanent ice. The great red spot is long gone, ceased billions of years ago when the atmospheric dynamics changed during the Sun's brightening and then froze entirely when the red giant phase ended and the weak light from the white dwarf proved insufficient to drive weather patterns. Jupiter's cloud bands have disappeared, replaced by a uniform layer of frozen hydrogen and helium, the temperature throughout the atmosphere near absolute zero. Jupiter's moons orbit the frozen planet in darkness, their surfaces unimaginably cold. Any liquid water that briefly existed during the red giant's warmth, now frozen solid once again, and likely to remain so forever. Europa's ice shell is meters thick in solid ice all the way down, no ocean remaining beneath, the tidal heating that once kept water liquid, now irrelevant with the internal heat long since radiated away. Ganymede and Callisto are similarly frozen, ancient cratered surfaces covered in ice that will never melt again, airless worlds locked in eternal cold. Io, once the most volcanically active body in the solar system, is silent and frozen, its internal heat gone, its surface covered in frozen sulfur compounds that once erupted from hundreds of active volcanoes. Saturn persists at roughly 10 astronomical units, its magnificent ring system long since vanished. The countless ice particles that once formed those brilliant structures, either fallen into Saturn's atmosphere or dispersed over billions of years by gravitational perturbations and radiation pressure. The planet itself is frozen like Jupiter, its atmosphere locked in ice, its once dynamic weather systems stilled forever by the intense cold. Titan orbits in darkness, its thick nitrogen atmosphere collapsed and frozen onto the surface, as ice, the methane lakes frozen solid. The organic chemistry that created complex molecules in the atmosphere ceased when the temperature dropped below the point where chemical reactions occur at any meaningful rate. Uranus and Neptune continue their distant orbits, frozen worlds circling the white dwarf at distances of 20 and 30 astronomical units, receiving almost no energy from the faint remnant star. These ice giants have become icier still, their atmospheres frozen solid, their interiors cold and inert, no residual heat remaining from their formation. The vibrant blue color Uranus and Neptune displayed during the sun's lifetime has vanished, replaced by whatever color frozen methane and ammonia present, though no light remains to illuminate them properly. Their moon systems orbit in the darkness, small frozen worlds that will never again know warmth or change. The Kuiper Belt objects, including Pluto and the thousands of other icy bodies beyond Neptune's orbit, remain essentially unchanged from their state during the Sun's main sequence lifetime, having been too distant to experience significant effects from the red giant phase. These bodies were always frozen, always cold, always dark, and the Sun's death changed little for them, except removing the faint sunlight that once reflected from their surfaces. Now they orbit in complete darkness, invisible except by their gravitational influence. Ancient relics from the solar system's formation era, preserved unchanged across the entire lifetime of the Sun. They will continue orbiting for trillions of years unless disturbed by passing stars or random gravitational encounters. The asteroid belt between the orbits of Mars and Jupiter has survived in altered form. The rocky and metallic asteroids still present, though many were lost during the red giant phase to the increased solar wind and thermal effects. These remnant asteroids orbit the white dwarf in silence, their surfaces bearing the marks of billions of years of impacts and radiation exposure, fossil records of the solar system's entire history. Ceres, the largest asteroid, remains in its orbit, a dark, frozen world that briefly experienced warmth during the red giant phase, but has returned to deep cold under the faint light of the white dwarf. Mars likely survived the red giant phase. Its orbit at 1.5 astronomical units, placing it beyond the Sun's maximum expansion. Though the planet bears dramatic scars from the intense heating it experienced when the Sun was brightest. The surface shows signs of melting and refreezing. Ancient landscapes, transformed by heat they had never known during the Sun's stable lifetime. Now Mars is frozen again, colder than during any previous era. Its thin atmosphere collapsed onto the surface. As frost, its polar caps expanded to cover larger regions of the planet. The ancient river valleys and outflow channels remain, testimony to a time billions of years past when liquid water flowed on this world. But those days will never return. Earth, if it somehow survived the red giant engulfment, exists as a scorched rocky remnant, completely lifeless, all atmosphere and water lost. The surface perhaps partially melted and re-solidified during the red giant phase. More likely, Earth was destroyed, consumed by the expanding Sun, or vaporized by the intense heat. Its materials scattered or incorporated into the planetary nebula that has now dispersed into space. The Moon, if it survived alongside Earth, would be similarly scorched and dead, or more likely destroyed alongside its parent world. The Earth-Moon system that existed for over 4 billion years most probably ended during the red giant phase, leaving no trace except the atoms that once composed these worlds, now mixed into interstellar space. The white dwarf continues cooling across timescales that dwarf even the Sun's 10 billion year lifetime, taking hundreds of billions of years to cool to a few hundred degrees above absolute zero. Current cosmological models suggest that after trillions of years, the white dwarf would theoretically become a black dwarf, a stellar remnant that has cooled to the point where it no longer emits visible light, colder than the cosmic microwave background radiation. However, the universe is currently only about 14 billion years old, far too young for any white dwarf to have reached this stage. And whether black dwarfs will ever actually exist depends on the ultimate fate of the universe itself across incomprehensible futures. The solar system in this final configuration continues to orbit within the Milky Way galaxy, the white dwarf and its retinue of frozen planets, moving through space as they have for billions of years, following a path around the galactic center that takes hundreds of millions of years to complete. The galaxy itself continues evolving, forming new stars from collapsing nebulae, those stars living and dying in their turn. The cycle of stellar birth and death, ongoing even as our own solar system has reached its final static state. Other white dwarfs exist throughout the galaxy, remnants of other sun-like stars, each surrounded by whatever planets and debris survived their red giant phases. Silent monuments to stars that once shone brightly. Occasionally, over millions and billions of years, the white dwarf and its planets might experience close encounters with other stars passing through the galactic neighborhood. These encounters potentially disturbing the orbits of the outermost planets or Kuiper belt objects. A particularly close pass might eject some planets entirely from the system, sending them wandering through interstellar space as rogue worlds unbound to any star. These encounters are rare but inevitable over the vast timescales involved, gradually eroding the planetary system until perhaps only the innermost worlds remain, or perhaps eventually leaving the white dwarf entirely alone. All planets lost to gravitational perturbations across trillions of years. This is the final state, the ultimate fate of our solar system and of most stars in the galaxy. The end toward which everything has been moving since fusion first began in the collapsing nebula billions of years ago. From the vast cloud of gas and dust through the ignition of the sun, the formation of planets, the long stable eras, the aging and swelling into a red giant, and finally, the collapse to this small, dense ember. The story follows a path determined by the physics of matter and energy and time. The same fate awaits billions of other stars, each following this pattern in its turn. The galaxy filled with these quiet remnants of stars that once burned bright. We have traveled through time from beginning to end, witnessing the birth, life, and death of the solar system across spans of time difficult for human minds to truly comprehend. The journey has taken us from the cold darkness of the primordial nebula through the violent birth of the sun and planets, across billions of years of stability and change, through the dramatic death throes of the red giant phase, and finally, to this quiet ending, the white dwarf cooling in eternal silence. Each era has held its own character, its own beauty, its own significance in the long story of matter and energy playing out across cosmic time. The story we have followed is not unique, but universal. The common destiny of medium-mass stars throughout the cosmos, repeated countless times across the history of the galaxy and the universe. Understanding this story helps us see our own place in the larger pattern. The temporary nature of the conditions that allowed Earth to host life. The certainty that everything we know will eventually end. And the continuity that links us to the ancient stellar deaths that created the atoms in our bodies. We are made of material from earlier generations of stars, and someday the atoms that compose us will drift in space again, perhaps to be incorporated into future systems forming from future nebulae. As we conclude our journey through deep time, we drift quietly through the outer reaches of the dead solar system, the white dwarf shining faintly in the distance, the frozen planets continuing their ancient orbits through the darkness. The violence and drama have passed, the transformation complete, leaving only this eternal twilight state that will persist far longer than any previous era. Everything has changed, yet the fundamental patterns remain, gravity still binding the system together, the laws of physics still governing the behavior of matter and energy. The white dwarf and planets continuing their journey through space and time into futures we cannot imagine.